Hello YouTube, I'm APC, and today we're going to be implementing an A pathfinding algorithm line by line in code. I'm going to be using GameMaker, however you can use whatever you like. As long as you have a pretty decent understanding of some programming language, you should be able to follow this tutorial without too many problems because, after all, most programming languages are very similar. However, before we get started, a word of caution. This is probably going to be the most advanced tutorial I've ever made. So before you go into this battle, there's a couple of concepts I want you to be familiar with, or at least be prepared to see in this tutorial. First off, loops are going to come up a lot in this tutorial. Make sure you know how they work, know what they are, and hopefully you've had a lot of exposure to loops already, but if you haven't, don't worry, you will by the end of this tutorial. The next concept I'd like you to at least be prepared to see is data structures. So data structures aren't something that's really taught in programming until you get to a more advanced level. It's not something people commonly learn. Particularly in GameMaker, it's not something that's commonly learned about or taught. I did a search on YouTube for GameMaker data structures tutorials, and there's a single person who's made a series of tutorials about data structures. So if you want to be more prepared, I'd recommend going ahead and checking him out. It's 2.5 Stooges. There's a link in the description to his series on data structures. Either way, if you're prepared or not for data structures, I'll be going through them slowly, so hopefully you'll understand what I'm doing either way. The next concept I'd like you to know about is the A pathfinding algorithm itself, or at least the logic behind it. I made a video explaining all this logic, so if you haven't seen that yet, go ahead and check it out. If you have seen it, go ahead and check it out again, so that way you can more fully understand the concept. And if not for that, also I made a error in the video, so if you go over there, you can see in the description of the video exactly what I did wrong, and you can go ahead and try and unlearn what I taught you. Yeah, it's kind of embarrassing. Oh well. And the last concept I want you to be prepared to be exposed to are a couple of, programming tricks. I've been programming for a long time, and over the course of my career, exposure, programming, whatever, I've picked up a lot of tricks that work well in specific situations. They're designed to make our lives easier, but they will probably look a little bit foreign to you. So just be prepared to see that. Again, like data structures, I will do my very best to explain this in a way that you'll fully understand what I'm doing. We'll take it slowly. So that's all the concepts I want you to be ready for. So I've got a lot of information available for you guys in the description, so go ahead and check that out. Down there you will find a link to my A pathfinding algorithm video that explaining the logic, as well as 2.5 Stooges' data structures series, as well as the source code of what we wrote today. Okay, now you are prepared for what is to come. There's no turning back now. Let's do battle. So for tutorials in general, and especially for very long tutorials, I like to break it down into several steps so that you can have an idea of where we are on the tutorial. So that way you get less lost, I suppose. So the first step we're going to do is to generate our field. So in my video explaining the A algorithm, we had blocks that you could travel through and blocks that you couldn't travel through. We're going to represent that by a two-dimensional array, and then each index will represent whether it's walkable or not. And we could, in theory, just set the values of the array to true or false depending on whether it's walkable or not, but we're going to do it a little bit more complicated so it'll be easier to use. So we're going to have it automatically generate the array based on where we place solids in the room. So we're going to spend a little time doing that in the beginning, so that way we can have our nice two-dimensional array to work with. So that's the first step, generating our field. The second step is doing the setup prior to the A. So in that step, we're not going to get into anything that I talked about in the logic video. I'm just going to set up everything for it. So basically do everything but the actual A. And then third step is to do what you guys came here for. We're going to do the A algorithm, or more specifically, we're going to do the algorithm which analyzes specific nodes, the 3 steps that I talked about in the algorithm video. Alright, so to get started, we'll make some placeholder sprites, so just so that I don't have to worry about it later. Make one for the player, or let's call him Pathfinder, because usually when I make tutorials and we have a player, you can control him, but I suppose you can control him here, but you can control him indirectly. It's not you, you're the person telling him what to do. So player would be, I guess, less good of a name. So I just made the image, and I filled it in yellow for the player, because yellow's a nice color. I like yellow. Okay, next one we're going to make solid. This is going to be what we're going to place on top of areas that we don't want to walk through. So we'll go make it black, a very uninviting color. And that's all for the sprites. I've never been known for making extravagant sprites. What did I just do? Okay, not exactly sure what happened there. But anyway, so we're going to create an object. We'll call this first one OA star. And while we're at it, we'll go ahead and let's make it a capital S. While we're at it, let's go ahead and make O solid as well. And we'll go ahead and set the sprite for O solid. We'll wait to make the pathfinding guy later. For now, we just want to generate the field. Okay. So in the create event, there's a number of variables we're going to be using in our A star. So basically, our A star object can do everything that takes care of the general variables related to our pathfinding algorithm, I suppose. So first off, we're going to make a variable called field generated. So when we're generating the field, we're going to want to look at each of the solids and look at their positions to decide what areas of the array we need set to true. But I don't want to do that in the creation event of A star, because it's possible that this code will be reached before the creation of the solid, which means that I won't be covering all. I may or may not be covering all the solids. So it's better if we do this step event. But I only want to do it once in the step event, so I'm going to use this variable to ensure that I only do it once. That's what that's for. Then a couple of other important variables: block size. This could be anything you want. This is going to be the size of the grid blocks, the width, I suppose. I'm going to go with 32. And then we have two more. So let's see. We know the size of each block, and now I want to know the dimensions of our entire field. So I want the field to take up the whole room. So the number of blocks depends on how many times this 32 fits in there. So what I'm going to do is I'm going to set field width equal to, let's see, we could simply do room width divided by block size, but the problem with that is we could end with decimals, and decimals can be confusing in this case. So what I'm going to do is I'm going to seal it, which means round up. So if it's 2.5, it'll become 3. If it's 4.75, it'll become 5, etc. So that way it'll cover a whole room. And similarly, I'm going to set field height equal to seal room height divided by block size. Alright, we have the dimensions of our array. And now let's create our two-dimensional array representing the field. So I'm going to call it walkable. So the way you work with two-dimensional arrays is you let's see, you put two numbers in here. So I put 0, 0, and that would represent the top left corner of my array. Just to give you a better idea of what we're doing here, here I have a grid. So this is how our 2D array is basically set up. So if I say 0, 0, as right here, then I am referring to this top left corner here. So 0, let's see, we'll say that's row 0 and column 0 is right there. And likewise, we can reference any index in this grid in that way. So you can make these individual boxes store pretty much anything, but in our case, we're going to make it store Boolean variables, which means true, false stuff, on or off. So right now they're all white, so we're going to say that means they're all true. In our case, white means it's walkable, and walkable is true when it's white. Okay, so so basically what I'm using to represent is the areas that are not walkable. So I can't go to spot 3, 3, because it's black. So we would set that position of our array to false, and likewise 1, 5 is black, so we set that to false. 6, 1 is black, and so we set that to false. So that's how our two-dimensional array is going to represent the field. All right. So I want to set each one in the false. So one way to do that is I could go through and type out each one, but I'm going to use some loops. I told you you'd have to be seeing loops, and I did not lie. So I'll just type it out and explain it later. You guys can erase me. Well, I guess I have an unfair advantage because I know what I'm typing. You guys are automatically at a disadvantage. Field height, J plus. Okay, I'm not staying true to my example here. Okay, how should we do this? Well, this is just how I do it, I guess. So I set up one loop right here, and that goes from I equals 0 until I is less than width, or for as long as I is less than width. So that goes through basically each column. So it goes to 0, then 1, then 2, then 3, however long the width is, that's how that works. And then the second for loop goes through each individual block in that column. So when I is equal to 0, when we're in column 0, we're going looping down through the blocks until height. So 0, 1, so we're at I equals 0, then we go 0, 1, 2, 3, 4, 5, 6, 7 with j, then I equals 1, then we go 0, 1, 2, 3, 4, 5, 6, 7 with j again, and in that way we kind of end up going da 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 da, and that's how we go through each block. And we want to set each block to false, so I'm grabbing index ij and setting to false. So that way initially we have a fully walkable grid. And then here in the step event, we're going to go back and set the ones with solids in them to false, to make them not walkable. Alright, so here in the step event. So by the time I make the step event, everything should already be created. So all our solids should be available to us for us to generate our field. So I am going to do, let's see, how am I going to do this? Well, first off, I'm going to check if the field is generated. So field generated. Actually, I won't put a not there. So if the field is not generated, then we do this. If the field is generated, then it's generated. We don't need to generate it. If the field is not generated, we need to generate it. Okay, so once we're in this if statement, then we're going to go ahead and set field generated to true. So that way the if statement is not called again. And we're going to go through each of the solids. So I'm going to say with, how do you spell with again? Okay, there we go. With solid. Alright. So what this with does is it'll say this piece of code in here, execute it in every single solid that we have. Okay? So with each solid we want to modify the controls walkable. So let's see if I say oControl.walkable, once it's equal to at some index, I want to set equal to false. So whatever index this block is at, I want to set that equal to false. Okay, so let's figure out what that index is. By the way, I have to say oControl because once this is executing in the solid, and once I'm in the solid, I can't refer to walkable normally because walkable can only be referred to from control. I called it control. I meant to say OA star. Okay, but you probably should you should know that by now. All right. Okay, now we're going to create two variables. I'm going to make them temp variables. I'm going to call one block x, and I'm going to call one block y. Okay, temp variables, by the way, means that they only exist within this area. We'll only use them here, so that's why I'm doing it. So I'm calling them VARs because that will make it more efficient because they'll only exist in this area, if that makes sense. All right, so block x. That is going to be equal to the x value of our solid, because remember we're in the solid, and I'm going to type down div y. Okay, div is integer division, so that means that if x over y is, let's say, equal to 2.25, then x div y would be equal to 2. They just cut off all of the decimal points and just take what you get. And we want our x and y to be whole numbers because the array only has whole number indexes. So, and by the way, if you are familiar with this, another way you could do this is that flooring x divided by y. That's the same thing, except this is slightly more efficient. So this would fall into the category of tricks you probably don't know. All right. And I did a terrible job with this. I wasn't even thinking. Okay, x div block size, not y. I don't know what I was thinking. Okay, this is going to be at y div block size. So that way, our x is represented as how many block sizes there are. So if it's x equals 64, that's 2 block sizes. Make sense? Perfect. Okay, and that should do it. And then here we're referring to block x and block y. And I believe that should do it for our field generation. Let me make sure and get the A star down here. Now this is highlighted because the variable now updated, variable name updated. Alright, now what I've been doing a lot in this tutorial is I'm going to be visually drawing things that I add in code, because right now you can't really see whether our code worked or not. So in the draw event, I'm going to add some code to draw out our field, and it'll show us whether we did our code correctly. Okay, And another thing about these draw things is I'm not going to type them out because it's just a lot of code and it's not valid towards the tutorial. So I'm just going to pause the video and you'll see it magically appear right about now. Alright, you can see it now? Good. Okay, so again, I have a two-dimensional loop because we're going to draw a square to correspond with each one of our walkable indexes in our array. So we're going through the same loop as we did within the creation event. I'm going to set my color to green, which I got a little bit of repetition here. So I could basically go up there. My bad. Okay, and then we're drawing a rectangle, and then additionally we're drawing text, which will represent which index of our array it is, which will come in very much handy later. In my rectangle, I'm drawing it from our index times block size to put it in terms of the room. Again, our j times block size put in terms of the room. Then we're adding 1 to get the lower right corner in this section. This should all be fairly familiar to you. Again, I'm assuming you guys know a lot of this stuff. I'm probably just going over needlessly too much. Okay, and then the last thing, whether it's outline or not, if walkable is true, we want to be an outline. If walkable is false, we want to be filled. And the reason I make this green instead of black is so that I can actually see whether this is being drawn versus it just being the solid it's drawn. And I draw text to represent which index it is. Okay, I think I said that already. I don't know why I went out of order. So let's go into the room, and we're going to throw a couple solids in there, and we're going to throw our A star object in there, and then we're going to play, and then this should work. Fingers crossed. Alright. Not to worry. Not to worry. I know exactly what happened. You're in good hands. Well, I guess if you're in good hands, it would have happened in the first place, but okay. Anyway, so block x variable in the solid. X variable, we're saying the x variable of the solid. Block size has never been created or seen in the solid, so it has no idea what we're talking about when we say block size. Just like with the walkable two-dimensional array, I have to say who the block size variable belongs to. So a star dot block size. A star dot block size. It's an easy pitfall to fall into, especially when you're doing those with statements, because technically you're doing in A star, so you expect to be able to have access to A star's variables. Okay, alright. I think I did this exactly wrong, like completely opposite of what I was supposed to do, because everything is filled in except the ones that we don't want to be filled in. No, everything is filled in except the ones we do want to be filled in. Alright, alright. Which is odd because I copied this code exactly. Alright, I want to initialize walkable to true actually, because initially we're going to have a whole field be walkable. That was my bad. A mistake done live. And this makes sense then. The walkable should be false. So outline will be false when this is called. How interesting. And let's also do this. Let's set the depth of this equal to -1, because I believe the depth of the solid was set to, or I think the solid was being drawn after OA star, which meant that it was being drawn on top of whatever we were doing, so we couldn't see anything we were doing. Alright, let's give this another shot. That is much, much, much better. Okay, so you can see every block has its own square. The ones where the solids were made are now filled in green. You can see, compare and contrast, which is exactly what we want. So we got our field generated just fine, and I think the gray color is ugly, so I'm going to change it to white. But we have completed our first step. Our first step was to generate the field. We have generated the field. Now our second step is to move on and go ahead and do the setup for our A star pathfinding. Okay, so let's go make our player now, because we need him, or our pathfinder. Very intelligent pathfinder. And let's see, we'll go into the step event. Basically, the usage of this guy is we want him to do nothing, and then when we click the screen, we want him to generate a path and then follow that path. All right. So in the step event, I'm going to say if we click the screen, or if we do mouse check button pressed, and that would be VK left. We'll do left, or any button, any key. I don't think that works. Is it MB any? Okay, yes, it is MB any. Yes, VK only applies to the keyboard. My bad. Okay, if we press anything at all, then we want to get a path, and we're going to say equal to A star get path. Okay, this is a script we're going to make. I'm trying to remember what exactly I set the parameters to. Okay, so we want a path from our x, y position, so where we are now, to wherever the mouse is. So mouse x, mouse y. Alright, and I'm going to go ahead and create a script for that one. So I called it A star. You get path, and just to organize, I'm going to add a description right here, which you will see right about now. So the first parameter is x value we want to start out, the second parameter is y value, and the third parameter is x we want to start at. Blah, blah, blah. I have descriptions here for each parameter, and note these parameters are in terms of the room, whereas most of our calculations in our algorithm is going to be done in terms of the array indexes. So there you go. That's that algorithm. That script right there. Moving back onto here. Once we have our path, that script is going to give us a path. We're going to go ahead and follow that path. So I'm going to say path start, and we want to follow a path, which will be the variable we just made up here. And we want to do the speed of, give me a number, I don't know, 5. I like 5. 5 is actually my favorite number. That works out pretty well. End action is 0. That means that we just stop at the end. And then absolute is equal to true. Okay. A star is going to tell exactly where we need to be if we're traveling from there to there. So we want to follow that absolutely, not just based off relative to where we are. Okay. And then I'm going to do some more drawing of debug stuff so we can see the path, which you will see right about now. So there's our code for that. We draw ourselves because that's kind of important, so we can see where the player is. And then I'm going to draw the path right here. First I check if we have more than 2 indices, because there's not really any point drawing the path if we have less than 2 indices. Sorry, more than or equal to 2 indices. Okay. Then I'm going to draw the path in blue, so I'm just going to loop through each index of the path and draw a line from the current index to the subsequent index. That's how that works. And then I'm going to draw a starting ending point so we can nicely highlight where we're going and where we're ending. So when I drew a circle where we're starting, made it green. When I drew a circle where we're ending, made it red. So you guys can go ahead and pause the video, type this all down if you so wished, or you can download the code. Okay. Yes, that is all for him, I think. I think that's actually everything we were going to do outside of scripts. The rest is all in our script world. Alright, let's go ahead and get this A star script taken care of. Alright, so we got, I'll make it like that, pre-algorithm. We have the algor, sorry, post-algor. There we go. Alright, let's get this up that we want to do done before we actually run our algorithm type thing. So, well, first off, we have all these arguments right here, and just having them in a comment doesn't really do anything. So I'm going to create variables to associate with each of these parameters. So I'm going to say var in lowercase v and ar, and I'm going to call start x equal to the first argument that we receive, so argument 0. And actually, to highlight my note here, I'm going to call that start room x. So again, these parameters are going to be the only variables in this script that is in terms of the room variables, and most of them are going to be in terms of our field indexes, which will make more sense later. I learned a trick recently from one of 2.5 Stooges videos. You can press F8 to zoom in. I think I'll do that. Make it easier for you guys to read. Okay, so start room y is going to be the same thing. It's going to be argument 1, the second thing that the user puts in, and then var end room x is equal to argument 2, and var end room y is equal to argument 1. There we go. Okay, now pre-algorithm stuff. So the first thing we're going to do is we are going to convert these variables we made here over to intermediate our grid. We did this once before when we were calculating the block x and the block y for the solid. I'll do the same thing here. So I'll create start x. I'll call it no, I'm not going to say y. Start x equals start room x div OA star dot block size. Okay, which again, this is basically just rounding it down. It's first dividing by this number to put it in terms of how many block widths we are from the edge, basically, and then we're rounding down to the nearest whole number. Okay, and then we're going to say start y equal to the same thing, start room y div OA star dot block size. And I generally don't approve of copy paste, but I'm going to go ahead and do a little bit here to save your time, and we'll make that one end, and we'll make that one end. So I made the above ones var because they're only used in this particular script, but I did not make these ones var because these are going to be used outside the script. Okay, so I'd like to make them var to save space, but I can't because they're going to be used elsewhere. So that's why these don't have vars. It's not a mistake. Now we're going to create create data structures. We have a whole bunch of data structures. Again, these cannot be var because they're going to be used outside the script. First off, G. This is going to store all our G values for all of our blocks in the grid. So this G, the data structure I'm going to choose for that, is going to be a map. So I'm going to say ds map create. So map is the type of data structure that we're going to assign to G, and when I say ds map create, I'm creating a brand new one of these data structures, and I'm assigning it to G. So G is now the owner of this brand new map data structure. Yep, he won it. He's lucky. Okay, next one is going to be H, likewise to G. So this one is going to be a map, and map I expect to be total gibberish to you at this point. Or I expect you to say that's where you find directions on, which is not true in this case, but you'll find out the true meaning in our context in a second, or a little bit, I guess. Okay, F is going to be a different one, so that's going to be priority create. Yes, okay, I got that one. Another data structure that we're going to be using, and then P, which is going to represent our parents. So for each block, we'll have a parent that it will, I guess, look towards, where that's where it came from. And this one's going to be a map, just like G and H. And then lastly, we have C, our closed list, which is going to be equal to ds map. ds list create. Creates a new list for us. List is actually the simplest of all these data structures, but we're going to be learning about all of these in just a moment now, actually. So, you guys are familiar with arrays. Yes, you guys are familiar with arrays. So, basic idea behind arrays is, I guess you can have array 0 equals 5, whatever. So you have a key that you reference by, so you have some key which represents some value on the other side, right? You have key value pairs, as you would say it. So list actually works exactly the same way as arrays. I have a key, I can say ds list find value, and I can input some key, or sorry, first I got to input the ID. I can look for some value in C, and I can look for some key in there, okay? So I ask for the value, and I'm telling you that value is stored at key. Just like arrays. Lists are just like arrays, except lists can do a couple of extra things. For example, let's say you make an array with 5 indexes. So if I do r0 equals 1, and then I copy that over and over and over, but do something like this. In a list, or sorry, in an array, if I said, you know, I don't want this anymore, I want to get rid of this, I get rid of this, and then we just have like empty spot in our array. It still takes up the same amount of space in memory because it's still 4 slots long. However, with the list, it will dynamically kind of shift everything that's after the 2 back down. So 3 would then become 2. So it keeps it all nicely numbered each time. That's what how lists work. And I told you guys about Stooges, 2.5 Stooges video. You can go ahead and check that out if you want a better explanation of lists. Okay, so map works very similarly. The difference is, A, your key does not have to be a number. With arrays and lists, your key has to be a number. And B, in addition to not having to be a number, it doesn't have that, it doesn't have to be, it's not really stored in a list fashion. Like, it doesn't have a first index or a second index and all that. It's stored in a different fashion. And the main reason why we do this is because, well, in G, we may not be storing all of our indexes. So, okay, let me see if I can explain this. So for each index of V, we're going to want to keep track of, I guess, which block, and we're also going to want to keep track of the G at block, I guess. So let's say we have blocks 1, 3, 5, and 19. All right. If we did this in an array and we referenced R19 or something like that, this is automatically 20 units long. But we only want to store 4 things, so that doesn't work with array. And we come with a similar issue with DSList, because in this case the keys do matter, whereas the DSList we're not worried as much about it. Alright, so we can store these pairs really efficiently. If we have 4 things with, no matter what their keys are, they'll be stored in 4 slots. So that's what's nice about maps. Okay, so that said, I'll talk about priority later. But for as far as the map goes, we want to add our first G value, because we'll be starting at the start, and we gotta go ahead and give it a value of G so that our algorithms will work. So init first G value. Okay. So we're going to say dsmap add, okay. And we're going to be adding to G, and the key is going to be, so remember, we have key value, and for our, basically our G, H, and R, P, the key is going to be which node, and our value is going to be the G/H/P value. Alright. So which nodes is kind of an odd issue, because if I ask you which node we're starting at, you'll say it's a node with a start value of X and a start value of Y. Or sorry, it's a node with X value of start X and a Y value of start Y. So you're describing it to me in 2 variables, whereas we want to add it in here as 1 variable for the key. Okay, so I'm going to make a handy dandy script called getKey, and that will take our 2 XY variables, and it'll kind of put them together in one variable, so we can reference it in these maps really easily. So we start X and start Y, and the value we want to give it is 0. Because remember, G represents the distance from our starting point, and the distance from our starting point at our starting point is equal to 0. Quite simply. Alright, so far so good. Let's make this handy dandy getKey function. I have a nice description here too. Takes in 2 numbers and returns a single number to represent the key. So it takes an XY and it gives back, I should probably add it here, returns key. Okay, let me go ahead and write the algorithm down. So I'm going to say return Y times OA star dot field width plus X. And what's nice about this is A, this is computation that comes down to 1 number, and B, each number has a unique key. Okay? And I'm going to go and explain this in more detail. I can refer back to my paint.net thing. Okay, so we're basically trying to figure out a way to number all of these boxes in a way that we don't get any repetition. So we can call, let's say we call this one 0, but then we can't call anything else 0. Okay, so I'm going to start off basically like normal. So I'm going to start 0, 1, 2, 3. That's a 3. Alright, so I got those ones numbered, and then I'm going to bump down, and I'm going to say I want to call this one 8. Alright, so here's the thing. Here our Y is 0, so Y isn't contributing anything, but our X is equal to 0, and here the index is always equal to our X, so if X is 0, make 0, X is 1, make 1, and so on and so on. So, and then in this column, we want our Y values to be represented. So our X can range between 0 and 7. So if we just let each Y value be equal to 8 be worth 8, let's say, that means that our x value will never kind of overlap with it. Our x value will never be equal to 8. So I'm going to make each of the y values 8. So 1 is worth 8, which means 2 is worth 16. Actually, that's not worth 32, that's 24. My bad. That's worth 24, 32, 40, 48, 46. Okay? So that's how they're numbered, and we can kind of continue on. So this will end up being 9, that'll end up being 10, that'll be 11, okay, 11, 12, 13, 14, 15, and then we jump back down and get 16. So you can kind of see how we number them like that, and hopefully you can see how my little equation ends up with this numbering. And also I hope that you can see why it is that we'll never get two pairs of, we'll never get two x and y pairs which end up at the same value. Okay? Because you can see that x ranges from 0 to 7, so if we make each y worth 8, that ends up doing it. This is not a very good explanation. You can kind of think of it as base 8 numbers if you so wish. That's where I got the trick from, at least. But important thing is this will give us another number for which no other pair of x, y will generate. Alright? And then while we're at it, I guess I'll go ahead and do the other way. So we have a way to turn x and y into a key, and I want to have a way to take a key and get the x and the y out. So I'm going to create a variable or script called getKeyX. It's a rather annoying error where if you have scripts that have similar like pieces and you type down the piece that's similar to something you already made, you get an error. I actually filed a bug report. Luckily, it's going to be fixed in the latest version of GameMaker. I actually need to update and that'll fix that error. That's what they told me in the bug report. Getting off topic. I'll go ahead and fill out the description for this one as well. Bam, and well, I'll do that one later. I'll do the other one later. Okay, this one is going to return. Alright, so if we look back to our paint.net thing, so we want to get the x out of it. Alright, so we've already said that these 8s, or these factors of 8, okay, each y value is worth 8. So what I'm going to basically do is I'm going to keep subtracting 8 until I get down to 0, and then what I'll have left is either 1, 2, 3, 4, 5, 6, or 7, which will be equal to my x value. Alright, so there's a fancy way of doing this again. I'm going to say, well, first, okay, my bad. First I gotta store this argument. I forgot to do that earlier. Var key is equal to argument 0, and down here, because the comment doesn't make it happen, so now I have the key, and then I'm going to say key percent field width, which I didn't say this either, but in our example 8 corresponds to the field width, so that's how this works. Alright, percent, which is the same as mod, gives remainder after dividing, because after all, dividing is pretty much the same thing as subtracting over and over again. So when we're dividing, let's say we divide this number, which would be 50, we're basically saying subtract 8 over and over again until you can't subtract 8 anymore without going negative, and then tell me how many times you were able to subtract 8. So if I have something like 25, subtract it once, twice, 3 times, and 25 divided by 8 is 3, with 1 left over, because there's a 1 left when you couldn't subtract 8 anymore. Alright? So 25, actually when you say 25 divided by 8, that has a quotient of 3, because 8 fits in there 3 times. And you have a remainder of 1. Okay? So when I'm saying key percent field width, I'm saying give me the remainder when key is divided by the field width, which in this case will give us our x component. Alright, I have a video all about mods if you are interested in learning more about it. So I'm going to duplicate this. I'm going to do something kind of semi-similar with getKey. That stupid error. Glad they fixed it in the next version. GameMaker's usually pretty good about fixing errors when people notice them. Did this last time too. Okay. How do I do this? There we go. That fixed it. That worked. Alright, takes a key and returns the y component. So the last time we were looking at the quotient. Last time we were looking at the remainder. This time we're looking at the quotient. So if you look at 25, its y value is 3, which is how many times 8 fits in there, which makes sense because we made our y's worth 8. Alright? So I'm going to do something very similar, only instead of using percent, I'm going to say div. And that will give us our value. That will give us our y value. Okay? And in getKey, I also need to initialize our x and y variable. So var x equals argument 0 and var y equals argument 1. Take in the arguments. And I probably haven't said this yet, but when you're working with scripts, when I'm saying return, that's what we give back after this is called. So if I'm asking to get the key, this is equal to the key, so I go ahead and give that back so they can use it. Okie dokie. Now that we got our key functions written, we can go ahead and use them here. Well, actually, we already used it right there. Perfect. Alright, so we have our g initializing, our start value at least. And now the last thing we do, actually no, that's it. This is everything we need to do before we run the algorithm. So we convert it over to a grid, then we create our data structures, and then we add one value to our G data structure. That's all we need to do before the algorithm. Now for the actual algorithm. The way this is going to work basically is I'm going to do a while loop, and we're going to keep running, or sorry, in each iteration of this while loop, we're going to analyze the node. Because if you saw in my video explaining the algorithm, you know, I started with one node, I went through the list of things to do with that node. Yeah, it was like, what was it? Add to closed list, and then analyze adjacent things, and then find one with lowest f value, right? So anyway, there's those 3 steps which I talked about in the A-star algorithm video, and that is done over and over again for each and every block until we find the answer. So while we're searching for the answer, so I'm going to write that here. I'm going to say searching. We're going to start searching to be equal to true because we're still searching in the beginning. While we're searching, we're going to, what shall I call this? Process current node. That's what I'm going to call it. I think that's a good name. Alright, and so this will go through that whole process which I talked about over and over again in that video for whatever our current node is. Alright, so I'm going to create some more variables. I'm going to say cur node x is going to be equal to start x, and cur y is equal to start y. Okay, so cur x and cur y represent the node that we're currently processing, and we want to start off currently processing the beginning because that's where we start when we're searching. That's how we talk about the algorithm. And then we'll run this for as long as we're searching, and in this script we're going to go through our process, and then at the end of our process for that node we're going to decide what we want to do. We could set search to false if we've reached the end, or if we run out of options, which will end the loop. Or we could set cur x or cur y as something different. We can place the recommendation to what we want to analyze next. So that's how that works. By the way, about that error I made in the algorithm video, if we had done it exactly the way I had explained it in the algorithm, we would have actually not done this in this way. We would have done it using a recursive algorithm, but as is, we are doing this iteratively, or with a loop, which is easier for people to understand usually. So I guess that's a good thing. And this is one of the things that I messed up, and you'll see specifically what that is later. Okay, so we're not going to go into this process current node. That's actually a third step. Third step is going to be all about writing that script, but we'll go ahead and create it just so it's there. Process current node. Alright, and here is what this function does. It runs through the A-star process on the current node. Okay. Let's see. In addition, we're going to add. Let's see. I'm going to add a found variable. So that's go false initially. That will also be set in this algorithm. Which, by the way, that should exist now, right? Yes, it does. Okay. So after we're done running through this, our big question is: so did you find one or not? If you found one, then we can kind of set up the path. If you didn't find one, then we're done, I guess. So we're going to create now we're going to generate the path, because all this processing does is it changes and works with all of these data structures. But we don't actually have a path to work with yet. We're going to look at these data structures, or specifically the parent data structure, to find out what the path ends up being. So I'm going to create a path variable. I'm going to set up -1 at first. And if we have found ourselves a path, then what we're going to do is follow the parents backwards to the start. So start from the end and go back until we're at the start. Alright. Which is what I did at the very end of when I was explaining the algorithm in the video. Alright, so I'm going to set up another temporary variable. I'm going to call it cur node. And our cur node is going to be equal to whatever our ending node is. So the cur node is just going to be one value, so it's going to be the key that represented by our end values, end x and y. And then we're going to do another while loop. So we're going to say while our cur node is not equal to our starting. And again, I'm using this get key so I can refer to it by one value, which makes things easier on many level. Alright, because at the end of the algorithm video, I followed the path back at the end, and I kept following it until I reached the start. So this is the saying when you stop. For each individual one, we want to add a point to the path, which first we need to have a path. We have this path variable, but it doesn't actually equal a path. This equals -1. So I'm going to set path equal to path add. Because this found variable is true, we know that there will be a path, so we can go ahead and create a path for that. Now the path has 0 points, but here in the start, we're going to go ahead and add the current node, which on the first iteration of this will be the end node. Alright, so we're going to say path add x, add point, that's it. Which path? This path variable was made. What's the x? Whatever the x value is of our current node, which is going to be get key x cur node, and likewise for the y, it's going to be get key y cur node. And then the last thing is the speed. So I don't know if you knew this, but in paths you can change the speed along the way. So maybe at in a straight ahead, you want the speed to be 100% of your normal speed. All right, but maybe you want to make it more like 50 in the corners. So the speed thing isn't actually saying how fast you want to go. You're saying how fast of your normal speed you want to go. So if the player is normally going at 5 pixels per step, then if this is 100, then it'll go with the full 5 pixels per step. Whereas if we set to 50, it would only be going 2.5 pixels per step. Okay, so we're adding the value of our current node. Now we want to kind of move the current node along back to wherever our parent is. All right, makes sense? So we're going to set our cur node equal to whatever the parent is of the node, cur node when it's up here. All right. So I'm going to find out what the parent is by looking in my parents map. So I'm going to say ds map find value. Is it value? Yes, because we know the key. The key is whatever our current node is, and the value of that is what we're interested in. Okay. So cur node is the key, and then MP is the map, and this will give us the value of the parent associated with cur node, which will be our new cur node because we want to move up to the parent. Okay. All right. So if we think about this, let's say this one is equal to the last node. So we're going through a few iterations. Let's say this is going to be the one that's equal to the one right before start. Then in this, it becomes start because this one was right before start. And then we go up here and check, and then we end the loop because we're now at start. But start never actually got added, so we got to go ahead and, once we finish that loop, we haven't added start yet, so we're going to go ahead and add start here. Path point add, or path add point. And we're going to go ahead and add start right here. So we're going to say path is path, whatever our start x is, whatever our start y is. Okay, I just realized something. This path is going to want the variables in terms of the room, right? But this get key x and this get key y and all of these things are in terms of the grid. Like I said, these are the only variables in terms of the room. So we need to convert these back over to be in terms of the room. So the way we do that is fairly simple. So the grid values, the grid x, represents how many blocks we are to the right of the left side of the room, and each block is a certain amount of pixels. So we'll just multiply that by the number of pixels in each block. So we say OA star dot block size, and I'll move this next line because it's getting a little messy. And likewise, I'll say OA star times the y value times OA star dot get block size, or dot A star dot block size. We're not working with getter setters here. And again, down here, we're going to multiply that by OA star dot block size, and OA star dot block size. Alright, and make that a lowercase t. Whew. And again, the 100 over here. Okay, almost done with this part. Okay, so now we have all of our points added from end all the way to start. But the problem with this currently is that, like I said, we have all the points added from end to start. When we're traveling along this path, we want to go from start to end, by definition. So we got to reverse our path. So I'm going to say path reverse, and then I'm going to say path. Okay. Another thing I want to talk about is whenever you create paths in GameMaker, they're automatically closed. So they automatically add a edge or a path, let's say, between your final node and your beginning node. So currently, the way it currently works is it will go from start to finish, and then from finish it'll go like in a beeline straight back to start because it's set to closed. We want to set it to not closed. We want to stop when it gets to the end. So path set to closed, path. Okay. Now that's set, I think. Oh, we want to set closed false. Alright then. Okay, so that is the algorithm process. I hope you understood that all. So we process all of our entire grid, so that our entire grid has like GHF values and P's and C's and everything. And then we go through this algorithm to generate the path based off of the line of parents back from the end. Okay, now at the end we're going to do post algorithm, and this is stuff we need to do after we're done to kind of clean up after ourselves. And there's actually only one thing we need to do here. We want to destroy the data structures. Yeah, it's sad, but our data structures have served their purpose. They've stored all the values we need, and now we no longer have need of them. And frankly, they're just a waste of space at this point. They are a leech on society right now because they're no longer serving a purpose. So it's just kinder, wouldn't you think, to kind of get rid of them. But yeah, in all seriousness, you want to destroy your data structures when you're done using them because they take up a lot of space in memory, and if you're not using them, that's a waste. Okay, so I'm going to destroy our G. So I'm going to say dsmap destroy. And I'm going to destroy G, and then I'm going to say dsmap destroy. And I'm going to destroy our H, and then I'm going to say ds priority T destroy, and I'm going to destroy our F. So all the data structures have their own destroy functions, and I'm just plugging in the data structure accordingly to destroy it. And you may need a reference up here to see what the data structures are. Okay, and then ds map destroy. We're going to destroy our parent map, and then ds map destroy, and we're going to destroy our C. Or that's actually a list. My bad, not a map. Okay, and then very last, we're going to return our result. We've generated this nice path, or rather, maybe not, depending on whether you found a path or not, but we've done the best we can, and we're ready to give back our results. So we can send it back to the Pathfinder, and then they can store this in their nice little path variable. Alright, so we're going to return paths so the player can use them. And with that, we have completed our second step. We have now generated our field, And we have done all the setup for our A star. Okay, unfortunately we can't test it right now because what we made kind of depends on this process current node script, but it'll be okay. We'll figure this out. Alright, so the process current node, this is going to be basically straight from the video, the algorithm video. Everything that all the logic you learned in that video is going to be applied in this very method. Okay, so let's remember the 3 steps from the video. So when we're processing a node, we add to current list, and then we analyze adjacent nodes, or I guess blocks or grid locations, whatever. And then after we've done that, we decide where to go next, right? Okay, this is the list. Unfortunately, with computers, they're kind of ignorant creatures. We have to spell everything out for them. They don't know anything. So there's a couple of things that were kind of obvious or I felt were obvious in the video, but we're going to need to spell them out for our stupid little computer here. Okay, first off, after we've decided where to go next, we're going to check whether we're at the end. Okay, the computer doesn't know any better. We need to tell them when we're at the end. I want to say that's the only extra step. Okay, well in my notes I have another sub-step here. And decide where to go first, I find best option, and then I decide what to do. Okay, so I guess we didn't have to spell out quite as much as I thought I did. So, add to current list, that's a terrible... Okay, close list, that's what I should have said, because now that we're processing this current node, we don't want to deal with it anymore. We never want to come back to it, because then we'd be going in circles, and that's never an optimal path if you're going in circles. So we're going to add this to the closed list. So the way we do that is we do ds list add. The list we want to add it to is list C, the closed list. And the value we want to add is our current node. So I'm going to say cur node. So if we go reference back here, what did I do? What do I do? What do I do? What do I do? What do I do? Okay, I have cur x and cur y. We don't actually have a cur node here. We have a cur node down here, but that's only temporary in this section. So I don't actually have a cur node, so I need to get that. So when I say cur node, I'm saying the key represented by our current x and our current y. All right, done. Add to closed list. We're 1/5 of the way there. All right, now analyze adjacent blocks. Okay, I'm going to do quick iterative for loop for I equals 0, I is less than. Well, actually, no, that's not what I want to do. I'm going to start out at cur x minus 1. I'm going to keep going until I get to cur x plus 2, or while it's less than cur x plus 2, and then do I plus. I'm going to do a better job explaining this in a second, by the way. For var j equals cur y minus 1, and j less than cur y plus 2, and j plus. Right. Okay, so we want to, I can pull this in PowerPoint, or not PowerPoint, whatever this is, Paint.net. So let's say we're analyzing number 11, so we would technically have 18, 19, and 20 right here. We want to analyze all 8 of these around us. So this is really basically a 3x3 square that we're looking at. Well, disregarding the 11, but basically it's 3x3 squares. And what's nice about this square is it's basically everything within this range and that range. Alright, so our current x is 3, so we're processing everything between 2 and 4 inclusive. Our current y is 1, we're processing everything between 0 and 2 inclusive. So that's what I'm doing here. I'm setting our range for the x to be our value minus 1, and we're going to keep going until we get to our value plus 1. A better way of doing this would be less than or equal to that plus 1. So the highest value we can be is that plus 1. Alright. Does that make sense? Alright, and hearing a yes, so I'll go with that. Okay, so this loop here basically loops through this area, this 3x3 grid. Okay. However, I need to make it a little more complicated, unfortunately. I'm going to get rid of my lines. What if I'm processing this spot here, block 0, 2, or I guess it's 2, 0, because we're doing x first, but yeah. Okay, then we'll do the same thing. For the y, it's, I'm sorry, for the x range, it'll be like that. We go from 1 to 3. For the y range, it'll be like that. We go from 0, -1, which is -1, to 1. What's the problem there? Well, when we're, what's going to happen when we try to look up these things with a negative y index? I'll tell you what will happen. We'll look them up in the walkable, and we'll get array index out of bounds because such values do not exist. Negative values do not work with arrays. They do not get along. So we need to make sure that under no circumstances do we go negative. Okay? So instead of saying cur x -1 right here, I am going to say, give me whatever's biggest, 0 or the cur x -1. So I'm doing max cur x -1. So if cur x -1 is 0 or bigger, then that's okay. He's always either bigger or equal to 0. Alright, so he'll always be chosen. However, the moment cur x -1 is negative, then it will, this thing will give 0 because 0 is then the bigger number. So going back to here, in this case, it'll start at 0 instead of -1. So this line actually is down here. So it actually goes to this 3x2 or 2x3, I guess. All right, and we can do the same thing for our y. I guess in my example that was for the y, but you get the point either way. We don't want them to go negative, and we actually don't want them to go above the field width or field height either, because we end up with the same problem. So we're going to do something very similar there. We're going to say min a star dot field width -1, because -1 is technically the highest index you can get to. And then here I'm also going to say min a star dot field width -1. Why do I have minus there? What's up? Yeah, okay. Okay, alright, so by adding these maxes and mins, we're ensuring that we don't get any array index out of bounds. We make sure that we stay within our grid, within our field. Alright. Okay. So as I mentioned a little earlier, when we have these grids, we are including ourselves. Alright. Now the current node, come into this already with a perfectly valid G value, perfectly valid H value, perfectly good F value. We don't want to change it because we're already set. Somebody else already took care of us in that front. So if this loop ends up on ourselves, so in other words, if our I is equal to our cur x and our j is equal to our cur y, then we want to skip this iteration. I want to say continue. So that's saying we're going to do a bunch of stuff here, but I want you to skip it all. I want you to continue to the next iteration is what that means. So in this way we can kind of pull that single exception out. The rest of them we want to analyze normally. So first thing I want to check is whether or not we can analyze this block. So by that I mean, well, first off, we need to be able to walk to it. Like, it can't be on top of a solid, but we're going to be referencing our walkable two-dimensional array. And the other thing we need to look at is if it's on the closed list or not, because if it's already been added to the closed list up here at some point, then we don't want to process anymore. We want to skip over it. We want to avoid circles. So var closed is going to be equal to whether or not it's on this C list. So that would be ds list. I'm drawing a blank here. I think it's get value, find value. Bam. Okay. So I'm gonna verify this second, but the way it works, I think, pretty sure, is actually doing find index. My bad. The way this works is, so we're looking in list C, and we're finding a value. So I know it's kind of confusing, but in our C list, the values are the nodes. All right, the nodes that we stored earlier. Because here, when we say add C, we're assign the value to here, and the index is just assigned depending on what just depends on how big the list is. So if the list is 5 long and you add another one, this will be put in the 6th position. Okay, so maps you can control the index directly, but it's not like that with lists. So here we're looking for the value, which represents the nodes that we don't want to go for. Okay, so if ij is closed, then it should be on this list. Alright, and I'm going to look at the reference real quick. So I'm going to go to index. I'm going to search something, ds list find index. Yeah. Alright, so right here you can see if the value does not exist, -1 will be returned. So it's closed when this is not equal to -1. If this is equal to -1, that means it's not on the closed list, so it's open. If it's not equal to -1, that means that it's on the closed list, therefore it's closed. So there we go. That's how closed works. We have 2 semicolons. Alright, and now walkable is going to be a little bit different. Okay, so first off we need to determine whether it's a diagonal or not. So if we're currently on 19, if we want to move to 12, then 11, 12, and 20 need to be free. Okay? Whereas if I want to move to 20, then only 20 needs to be free. So for as far as walkable, if it's diagonal I need to check all 3, and if it's to the side, then I need to check only 1. Okay. Okay. So let's see. Let's determine what's diagonal or not. There's a neat little trick for this, which I'll explain. So diagonal is equal to I plus j percent 2 equals cur x plus cur y percent 2 there. Okay. Alright. If they're diagonal, then these 2 values will be equal. Okay, so what are these? So this is saying this is modulus, right? So if I add these 2 and I divide by 2, what's my remainder? So first note that my remainder can only be 0 or 1, because if it's divisible by 2, then it's 0, because it divides fully by 2, there's nothing left after dividing by 2. If it's if the remainder is 1, that means that it's not divisible by 2, because after dividing by 2, you get 1 left. Alright? Another way of saying this is that if this value is equal to 0, then this sum right here is even, whereas if this sum here is equal to, or this equation here is equal to 1, then it's odd. So what this is saying is they're diagonal if they're both even or both odd. Let's see. Hopefully I put the numbers in a different layer. I did not. Okay, let's get rid of these numbers real quick. Okay, so I'm going to go through this grid, and if it is odd, I'm going to fill it in green. Otherwise, it's going to stay white. Okay, so let's look at this spot right here. That 0 plus 0 is 0, which is even, not going to fill it in. Let's look at this spot. 1 plus 0 is odd, fill it in. 2 plus 0 is 2, which is even, not going to fill it in. 3 plus 0 is odd, and keep going like that. No, for the first line, it's just whether the number is odd, xi is odd. Right. And then for this one, 1 plus 0 is odd, 1 plus 1 is 2, which is even, and we keep going like that. If you keep doing that, you'll find that you get like this perfect checkerboard pattern, which makes sense if you think about it, because if we're, let's say, for one thing, if we want to even and we add 1, it becomes odd, right? If we want to even and we subtract 1, it becomes odd as well. So let's say we're on spot 2, 3. If we go up, we're subtracting 1 from our y, so which means we're in turn subtracting 1 from our sum, so it becomes odd when we go up. If we go down, we're adding 1 to our y, so in turn we're adding 1 to our sum, which means, again, we're becoming odd. And the same can be said for left, right. So if we go up, down, left, or right, then we are switching either from odd to even in this case, or from even to odd if we're starting from white blocks. I think just now I explained this wrong, but you get the point. By going to the sides, you switch parity, that's how you'd say it, you switch from even to odd or odd to even. If you go diagonal, you're actually making two changes. So if I go diagonal up and to the right, then I'm adding to the x and I'm subtracting from y. So nothing's happening, that's adding 0. So I maintain the same parity, I maintain odd in this case. If I go up here to the left, I subtract 1 from x and I subtract 1 from y. I subtract 2, I remain odd. So you can see there's that nice little pattern where we can see whether diagonal or not, see whether our parities match. Okay, so this checks even or odd, and if these match, then we're diagonal. Pretty simple. Okay, so if diagonal, we do something else. Do something else. What I'm trying to determine here is whether we'll say can walk. We'll just start off with false. Okay, so if it's the sides, it should be it's pretty relatively easy because with the sides, it's just you're only checking that block you're going to. So if this ij is to one of our sides, we can just set can walk equal to the walkable, let's see, whatever the walkable index is from our OA star. So walkable, and that's ij. Okay, this is gonna be a little bit trickier. Of course, we need to be able to walk to it, so we can add we can start with that can walk equals OA star walk ij. Okay, so if we go back over here, if we're analyzing this one, 2, 3, that's our current node, and we're checking out 1, 4, we need to check these 3. In other words, we want to check 1, 4, and 1, 4 with the x value the same as our current. So with the x value the same as current, or we're checking 1, 4 with the y value changed to the y value of current. Make sense? And that can be generalized to anything. So if this is our current node, if 2, 3 is our current node, and we're processing 1, 2, if we change the x value to be the same as our current, we'll be looking at that one. If we change our y value to be the same as our current, we'll be looking at that one. So that said, we process the one we're processing, or we check the one we're processing, whether we can walk in that, and we check it as well with the I changed to our current, and we process it again with our j or our y set to our current. Okay, does that make sense? I hope so. So notice I've used ands here the whole time, which means that this and this and this need to be true in order for this to be true. So these all need to be walkable in order for us to be able to walk to that diagonal. Okay. All right. So if not closed, if this current one analyzing is not closed, and we can walk, then we can move on. So now we're actually analyzing this for reals. So we can go ahead and let's go ahead and start calculating our G, H, and F values. So this will be, so we'll start with, or I'll call it temp G, because we may or may not keep this. This current G hasn't gotten an offer yet. It hasn't joined the band yet, whatever. So that's going to be equal to, I'm going to actually create 2 more variables up here to make things a little clearer. G represents the distance between the node we're processing and the start. Alright, so I'm going to look up dist from start. Dist from start to current. I'll make that a variable, and that's going to be, and then we're also going to make a variable called dist from current to ij, or the one we're currently processing, or the, so I keep missing, okay, current or the one we're processing. Okay, so the distance temp G is going to be equal to whatever the distance from start to current is, from start to current, and then from that we add the distance from current to ij, dist from current to ij. Does that make sense? So if our path, let's say our path starts there. We are currently analyzing, our current block is that one, and we're analyzing this one. So we'll say we traveled along this path to get from our starting point to the current point, and then from the current point in order to get to the one we're analyzing, we would do something like that. That makes sense? So by adding the two, we find out what distance we traveled to get from the start to the one we're analyzing. Does that make sense? Good. I just heard a resounding yes. Alright, so that's why we can do this. So let's figure out how to calculate these. This from start to current, that is going to be whatever the g value is of the current one we're looking at. So that would be okay. We have that. It should be in our g map. So I'm going to set ds map find value, and then down here it's asking me, okay, which map and which key. The map is g, and the key is whatever our well, I suppose it's get key cur node x and comma cur node y. Alright, and actually, if you think about it, we don't need to make this, like, we can pop this variable up here because this variable depends on ij, so we have to do it inside this for loop because this is where ij, because this is where the ij is changing, I suppose. But this cur node x, cur node y doesn't change out this entire script, so we can just go ahead and calculate that beforehand. We don't need to recalculate it each time, or we don't want to need to relook it up each time. This, however, we do need to recalculate each time. So let's see. This is going to be equal to how should we do this? Well, I suppose it depends on the diagonal or not. So I think I'll pop this up here. I'll initialize up here, use it equal to 0, and then if we're diagonal, then just from current is going to be equal to, let's say, or if we say the width of each block is 1, then the diagonal is going to be the square root of 2, because if you take the triangle, or the distance formula, I guess you get 1 squared plus 1 squared and take the square root, end up with square root 2. So we could say sqrt2, but it would be a waste to have to recalculate the square root of 2 every time, especially because it's not changing, it's always the same thing. So let's see if we actually look up what's sqrt. Oh geez. If we have to actually look up what sqrt, which is where is it? You guys are probably staring at it right now. There it is. Okay. Oh, so okay. So I say 2. No, 2. Take the square root. Okay. 1.41421. Let's go ahead and do that because I like to be exact. 1.414. Now I'll do 414. That sounds good enough. 1.414. Alright. That's what the distance from current is. Or sorry, distance from current to ij. And then we're going to say dist from current to ij again, and this time it's only going to be 1 because when we go to the side, we're only moving 1 block over. It's not a diagonal distance, so that's that. Okay, now we have temp g. Now temp g can be calculated. Alright, and temp h, which should be a little bit easier for our temp h. This is the distance from our ij to the end. So we're going to do that using the Manhattan method. We could, if you wanted to, or okay, insert heuristic of choice. We use Manhattan. So the way Manhattan works is we take the difference in the columns and difference in the rows and add them. Alright, so the difference between our ij and x and y, or sorry, the difference between our I or our column versus the end x is going to be the abs of I minus end x. Okay, then we can add the difference in the rows, which is going to be j minus end y. Alright, note, you could also use point distance ij and x and y. This is also, I guess, it's also not exact, but this takes into account the straight line distance, whereas this takes into account if you're going kind of more to the side and up. So that's just different ways you can do it. I think this is more general in a grid form because, actually the fastest way you can go is to the side and up. Well, I guess that depends. You have much less flexibility in terms of going in a straight line in the grid than in here, but This is also just different heuristic. Just thought I'd throw that out there. Okay, and the last one of our temp f is equal to the sum of our temp g and our temp h. F, that's what f is. It's the sum of those two. Alright, so what we just did there is we calculated g, h, and f. Okay, so whether or not we actually use them depends on a few factors. Let's see, I'll call this section update if necessary, and I'll tap this out. Okay, factor A, have we processed it? So has this current ij already been processed before? So if processed, okay, so processed is going to be equal to, well, if we processed it before, it should be one of our maps or one of our lists. So remember, in the beginning, we added the starting node to our G list or our G map, and it should, in theory, stay there. Sorry. So if it's in the G map, that means we processed it before. Okay. So we're going to check that. DS map exists. Yes, that works. Okay. So we're checking if a certain item exists. So we're looking at G, and we're looking for the key, get key ij. If that key exists, then it has been processed before. If that key does not exist, it has not been processed before. So, you know, if we have processed it before, we do something rather, but if we have not processed it before, go ahead and add the stuff. Let me go ahead and look up this DS map exists. I'm not sure it's the same way I did it when I originally designed this, so I'm going to look it up. I'm new to using these things too. I've learned about them before, but this is my first time using a GameMaker. Alright. This function will return true if a specific key exists in the previously created DS map, and false if it does not. Alright, that's simple enough. Then we're good. Alright, so as you can see, no matter how long you are in GameMaker, it's always nice to look up contents, and you shouldn't be ashamed to do that yourself. Now, we need to do something in here. We need extra stuff in here, but we'll go ahead and do this stuff what we do when it's not processed, because if it's not processed, it's fairly simple. If we haven't processed it before, then we're going to want to use these values up here. Alright. And the way we do that is, well, okay, we add them each with respect to map. So temp G goes into the D map. So ds map add. We're adding 2G. The key is going to be the key of ij, and the value is going to be our temp G. Likewise, we add to the H, our map. We're adding H. We're going to get the key ij, and we're going to get temp H. Our F is actually a priority queue, so I'm going to say priority add, and we're looking at F. We're going to get key ij, just the same, all the same, and we're adding temp F. All right. Okay, that's how that works. And also, by the way, we need to set the parent to us. So when they travel to this node, they're traveling through us because, you know, they've never had any candidates before, so we're just the only candidate, so kind of get it easy. So in that sense, you're going to say ds map add, that's p, again, get key ij, and the value is going to be the parent of this node, which is going to be us. So get key cur node, that's why in this one text. Bam. Okay. There we go. Alright, now processed. So, when do we want to update them if they have already been previously processed? Well, we only want to update them. If the new f that we find is better than the old f. So what we would do is, I suppose, we would look up the f that's currently stored in that variable, and then we compare it with this temp f that we found, and see which one's lower. And if our temp f is lower, then we're going to make this list of values the new one, because this is clearly better. Okay. Let me kind of talk about something. So I've made f in a priority queue. It says priority short in the method, the function names, but it's a priority queue. And I've made G and H in maps, even though they kind of work the same way. We're just adding it to it. Why did I choose to make f a priority queue and G and H maps? All right. Well, if you ever take data structures in school, one of the things that you do is you analyze all the operations you can do with the data structures and how efficiently you can do them. So for map, you can remove elements, you can add elements, and you can look up elements. Okay, same for priority queue. You can remove, add, look up, and all that. So for map, the thing is, it's much faster. I think in general it's much faster to look up. For looking up values, it's better to do that with the map. Map has a better efficiency for as far as looking up values than priority queue does. All right. The reason why I use priority queue with F is because priority queue, its claim to fame is that you can look up the smallest value really fast, like extremely fast. You can find the smallest value or the highest value, however you want to set it up. But it organizes them so that the more extreme the value you're looking for, it'll list those first. Okay, so it's easier to look up values at the extremes. Usually when you're setting up priority queues, you will set up to go with either easily look up maximum values or easily look up smallest values, but GameMaker seems to go both ways somehow. So yeah, we use priority queue for F because we can find the smallest F real quick, which is something we're going to be doing later, and we use maps because we can look things up better in general, and we don't necessarily need to find the smallest G or the smallest H. Okay, so what I'm saying is we are looking for which F is smaller, but we don't want to do a lookup from our priority queue because that's less efficient than doing a lookup from the map. So if you think about it, this temp H we calculated here will not be any different from the H that's already stored in the list for this particular block. Because it's Manhattan heuristic distance thing, that this equation will not change depending on, cur node x and cur node y do not come up in this equation. They do not affect the difference. However, cur node x and cur node y do affect the g. So, and since f is just g with h tacked onto it, we should get the same answer comparing g's as we would for comparing f's. So instead of comparing the f values, we're going to compare the g values. Alright, and so what I'm going to do is I'm going to say if dsmap find value for our inmap g and get key ij, if that is greater than our temp g. Alright. If the g that's already there is bigger than our current g, that means that our current g is better. So we're going to update the value stored here to be this current g, as well as everything else. Actually, we're going to do pretty much exactly the same thing as we did down here, so I'm going to go ahead and copy that. Alright. The difference is that we're not actually adding anything. Like, these are all dsmap add. Well, these are all addings, but we don't really want to add them. We want to update them or replace them. Actually, these functions all have alternate version, which is called replace, which work the same way, like exactly the same way. The documentation even says if you're replacing a value that's not there yet, it'll add it. So technically, we've used replace the whole time. But yeah, you get the point. Let's see, I was hoping I made a typo here, but turns out that ds priority replace doesn't exist. Well, that's a shame. Maybe it's called update for priority list. No. Okay. Let's see, let's give you some hints back there. Add change priority, that's what I want. So we're changing the value. Alright. So that key is going to have new value to have. Alright. That should do it. So we update the parent as well because now we have a new best way to get to this ij. I think I'm going to make a separate variable here. Var better g equals all of this stuff. You probably notice I've been doing this a lot. It just makes everything quite a bit easier to read, in my opinion. So instead of trying to read this and trying to dissect what it means, you could just see better g. Or I think it's called lower g would maybe be more accurate. There. Okay. So So this just makes things more easier to read. I mentioned this in a quick tips about if statements. This little trick of pulling out the condition. Alright, now we check all our adjacent nodes, we determine whether we can walk to it, and if it's not closed, and if it's available, we'll go ahead and check what the values are, and then depending whether it's processed and whether the new G is lower, we will either add or replace the values, or do nothing. We might just do nothing. Okay, that is all for this step in our algorithm. Okay, find best option. This is going to be like probably the easiest one yet. So var, let's say min f. So the smallest f value, like I said, the reason why I use priority queue for f is because it's really easy to find the smallest value for priority queues. So we're going to look for the smallest value thing, ds priority, and what is it? I'm going to cheat here. I'm going to say delete min, because we also want to remove it from the list. So that way, you know, we're going to be using the min f. So next time we find the smallest one, we don't want to give it this min f because we've already consumed it basically. So you know, delete min, what it does is it gives you the smallest and deletes it. Whereas if I think it's find min, that would give it to you and not delete it. But we want to delete it because we don't want future calls of the script to use it. Okay, and the ID is f. Bam. Okay. So this makes things really easy. When I was designing this tutorial, I had to write like 15 lines to you know, scan through and find the smallest f. But this is just really nice. We can use this to help us out. Actually, a problem of mine when I was making this tutorial is that I didn't have it searching through the entire f list. I had it only searching through adjacent nodes, which is what I thought that was the way to do it. And that's also the way I explained it in the video. But you guys remember in the beginning of my A-star algorithms tutorial, I referenced an article written by Patrick Lester, and I said that's a really good article. It helped me to understand this. Well, I was having these issues with only checking the adjacent nodes, and I actually emailed the author and of that article. And even though he wrote that 9 years ago, he got back to me and he explained to me what I was doing wrong, and it turned out that I was just thinking about it the wrong way. You don't look through the adjacency nodes every time. You look through all of the nodes listed in F. So that was kind of an embarrassment for me, because I've been using this for a year, and I only just found out a few days ago that I've been doing it wrong this whole time. And I put something on YouTube that was wrong, but I explained it in the description. So hopefully I won't screw too many people over like that. That change is quite nice because I'm looking through the same list each time, and because the list doesn't depend on which node I'm currently on, as it would if I was looking through adjacencies, I was able to change implementation to be iterative rather than recursive. And recursive, I like recursion, but a lot of people think it's difficult to understand, so it's probably better this way. And I get to take advantage of this cool function, which I wouldn't have been able to do otherwise. Okay, so now decide what to do. So we want to figure out whether if min f found something. I'm going to look at the documentation again. I'm going to figure out what ds priority delete min tells me if, like, there's no mins in there, just if it's empty, basically. So ds priority delete min. That's you. Okay, this function will turn the value of the lowest priority and then remove the item and priority from the data structure. If more than one value has the same priority, the one that was added most recently, queue first will be removed, but all other values with the same priority will still be in the queue. Doesn't tell me what it does when the queue is empty. GameMaker API isn't always the best, but it's usually pretty helpful. The above code checks an instance variable, and if it returns true, execute the script. Okay. Well, that's good that we checked it then. So actually we should be looking for ds priority empty. That's the one we want to use. So that one should be fairly straightforward. This function can check whether the queue is empty or not. Turn true or false accordingly. Okay, so before we we set that, let's go ahead and set minf equal to -1 at first. And we only want to update it to the smallest value if the list is not empty. So if, well, I'll create another var here called empty, and that's going to equal to ds priority empty, and I'm going to use f as my ID. That's the priority list that I'm checking to be empty. If it's not empty, update it to whatever the smallest is. Okay. So decide what to do. Let's go through our options. If our minf is equal to -1, if there's nothing left for us to use, then we're gonna have to end our search. So if we go back a little bit in here, I created these two variables which are accessible in this script, and those will represent whether we're still searching and whether we've had a successful search or not. So down here we are no longer searching, so searching equals false, and we have not had successful search, so found equals false as well. That's all for that. So else, if we did find something, then what are you waiting for? Let's go there. So we're going to set our cur node x equal to whatever the x value is of our minf, which is get key x minf, and our cur node y is equal to get key y minf. So let me back over here. So what that code is basically at the end, like resetting the cur node is basically at the end of the script. So when it jumps back out here to this while loop, it'll go back to the beginning of the script and it'll run through the same process again with that new cur node x and cur node y. Okay. And then at the very end, if this minf is our final node, then we want to stop. Okay? We've had a successful search. So if cur node x is equal to end x and cur node y is equal to end y, then we want to end our search. So again, we're going to set searching equal to false, and this time we're going to say found equal to true. And that, ladies and gentlemen, is the A* pathfinding algorithm. We have walked through the whole thing in about 67 lines, and with another 65 over here. I hope you guys understood it. This went pretty smoothly, I think, but I mean, this is like the 5th time I've written one of these, so I've gotten pretty good at this point. I'm pretty happy, but I can imagine that's kind of confusing looking at it for the first time. Hopefully I was able to take you through this process semi-smoothly. Okay, so now we are pretty much finished. All we need to do is test it, or rather, we're about halfway done. The other half is about to come, the testing, probably. Yeah. I was going to say it, but it beat me to it. I was going to say it'll be a miracle if we made it through here without errors. And miracle has not happened. So it says, it calls, okay, let's look at an object pathfinder. So in the step events right here, this error is saying, in event number 1, action line 2, function A*getPath is called, expects 3 arguments, so we provided 4. Okay, so in here, indeed we did provide 4. That's because we want it to have 4. We want to have an xy for the starting position and an xy for the ending position. But this error thinks that it should only have 3, so we must have done something wrong back in here, which indeed we did. We pulled in argument 0, 1, 2, but not 3. That needs to be a 3. That there is the curse of copying and pasting, because if you try to change things, problems happen. Actually, I don't think I even copy and paste those. I think I just wasn't paying attention. Okay, I closed out the compile window. I thought there was a second error in there. No, there's not. There is not. This is a rather huge window. I think I'm going to make the room a little bit smaller. Oh yeah, that's right. In the past update, they changed the default from 640 by 480 to 1024 by 768. I read that. I forgot about that though. Thought it seemed big. Well, I like 640 by 480 personally. Okay, and then put that there. I thought they were supposed to fix my glitch in this update. Wait, was it this glitch? No? That glitch is still there. The guy told me to fix my glitch. Or no, get key. No, it's still there. No. Oh well. I guess it's next update that he was referring to. Now we need to add a player to the room. Or the Pathfinder. Oh, he's there. Okay, we did that. Okay, now let's test it out. Sorry, I got a little sidetracked there. Okay. Sorry, just another pet peeve of mine. I want the player to be above everything, because he's important, you know? So we'll make it -2, because I think we already used -1 on the control star. Yeah. Now I just have everything. If I click 6-5, hopefully it should walk in a straight line towards 6-5. No, it will not. Miracle has not occurred. It does not know what I'm saying when I say cur node y. And I'm referencing it in here in the process node script. Alright. So, oops. Okay, whatever. I remember where it was anyway. I was planning on keeping that open, but okay. So that was that was right here. That's where he's unhappy with it. Does not know what cur node x is and cur node y is. And I did not reference it earlier, so I think it's these cur x, cur y, but let me look into it. Yeah, I was saying I have not referenced it earlier, so it's likely that future things would invoke the same error. And yes, it does look like I named him cur x, cur y. I think in my test runs I was naming him cur node x, cur node y, so that's why I was messing it up. You guys are probably looking at me the whole time, cringing every time I made that mistake. Well, I did it correctly here. I did it correctly here. And here, and here. Do I have any more cur node x's? Yes, I do. That's gotta be cur x. That's gotta be cur x. And likewise, you gotta be cur y. And anyone else? Yes, we do have some other takers. You go away. You go away. Never panic with errors. They're simply friendly messages from the compiler or the program telling you what you did wrong. Errors are your friends. Sometimes friends can be annoying though. Doesn't know what end x is. It's probably a similar issue. Let's see. End x I also created up here. I created it over here, but as you can see, I did not actually make a variable called end x. They're both called end y. So that'll do it. Okay. Yeah, same thing. Well, this one's similar because I made the error, different script, but you know, naming consistency error. Okay, if I click there, another error. Filed width. Okay, this one I know what the error is too. If I go to get key x, I need %key field width, which is what I want, but field width is a variable from the OA star object. So if I type OA star dot, that should fix that. And likewise, I believe we got y probably the same thing. So OA star dot. Yep. Just me not paying attention. What else is there? You guys see that? Look, he went straight. I'll show you again. He went in a straight line perfectly. Okay, I was about to say this is the first time implementing this without any logic errors whatsoever, but we got something, which is fun. You guys get to see how more difficult things. Okay, let's see. So he's walking fine there. Let's see if we can find a pattern. He doesn't seem to be able to go up or down, but if I go to the sides, he's happy. What if I go like more diagonally? Yeah, you can go diagonally 1 block. 2 blocks? No, not 2 blocks. Interesting. Well, it looks pretty cool. The pathing is being drawn okay. So I got a ton of these logic errors, by the way, in my game, and I'm not sure I've gotten this one before, so I legitimately have no idea what the error is, but that's part of the fun. I don't like it for you guys to think that I can just, out of my head, make an A pathfinding algorithm 100% flawless right out the bag, because I can't. There's errors, and I think it's important for you guys to learn the process of debugging as well as the process of creating code and using cool logic tricks. Alright, so the way I tended to debug these logic errors was to so in here, and this while loop runs several times and it goes kind of all over the map, and we want to get an idea of where it's going. So down here, every time it makes a decision, I'm going to say show message. Like right here, I'm going to say, let's see, so in here we are deciding to stop. So I'm going to say where we are. So I'm going to put parentheses there, and I'll put the x value where we are. So get key. Actually, I can say cur x plus comma plus cur y plus and then we'll say no more nodes left, something like that. We're crying. And then this way a message will pop up whenever it gives up on the path, and I can know what it's thinking, kind of. So that way I don't have to guess at it. And something weird in GameMaker is string concatenation doesn't work very well. Like, string concatenation works, but they have to be strings that you're concatenating. You cannot concat. You cannot concat integers to strings. So since these are numbers, we cannot mix them with strings. So I have to make sure I convert them to a string first beforehand. All right. So I'm going to go ahead and add messages like these to all of the main sections of the code, and in addition, I'm going to create a variable called debug. So that way, I'm going to say if debug, do this, and then up here I can create that variable var debug equals true, because all the windows get very, very annoying after a while. Okay, and I'm going to cut out for a second. I'm going to add all those extra messages. Okay, all done. So I've added 3 messages. One when we found the final node, one when we're transitioning to another one, and one when we've given up, when we're out of options. I may add more, but for now, let's see what happens. See if this gives us enough information to find out what the error is. Okay, so let's first off see what should happen. Okay, so we already have an issue. My bad. I said, hey, we're at cur x cur y. We're gonna try out cur x cur y, which I should have said whatever the get key is for f min, or min f. My bad. Key x. Brilliant. Alright. Now we should be able to, it should go the way I want it to. Alright. Click here. This says, hey, we're at give me a moment. Alright. So I cut out there for a second because I was thinking I was printing it out wrong, because it kept saying we're at this cur x cur y, and we're trying out with a min f min y. And I was kind of frustrated because I don't know why it's doing that. So just now I was about to say, so it looks like we have a hard error on our hands, but as I was saying, I saw the issue, so it's not that hard. I created this variable code cur node y, and I should have taken that away. I should have fixed that earlier, and it's down here too. Do we have any more cur node y's in the house? Because we shouldn't, hopefully. Okay, yeah, so always be calm. Well, actually what's happening is I'm updating my current x and y before I'm jumping into here. So I want to print out what's happening before I change these cur x cur y. That's the deal. Okay, now let's click here. Now it's making more sense. So 2, 5, x2, y5 is right there. That's where we are. From that node, we're saying, hey, let's try out 3, 5, because that has the lowest f score. Because clicked on 6, 5, so 3, 5 is the closest to 6, 5, and it has a reasonable g value. So that creates the best f score. Okay. Now we're on 3, 5, and we're trying out 4, 5. So I wish I could color this, but it would have taken a long time. But so when we're searching for everything, we're looking for everything we've processed. So on the first one right here, we've processed everything in this little 3x3 grid. From 3x3, 3x5, we've added these 3 over here. And so now we're looking through everything here, with the exception of 3, 5, and 2, 5, because those are now closed because they've already been processed. And looking at all those, 4, 5 is the best. Okay, so now from 4, 5, our list keeps getting bigger because now 4, 5 added these 3 to the list. Now 5, 5 is the best. and then 5 5 says 6 5 is the best, and then 6 5 says you found me on the final block, and then let's see, and then our algorithm follows the parent back and finds that path. Okay, so vertically wasn't working, so we try to go here. Let's see what happens. So 6 5, which is where we at, trying 6 6, which it shouldn't because 6 6 is the closest one. 6 6 tries 6 7, 6 7 tries 6 8. You found me. Brilliant. I think that cur_node y variable misname thing might have just been the issue with that. So if I go here, okay, this is why I have the debug variable, so I can turn this off if need be. It looks like it works. Let's see, I'm going to go into A star and I'm going to actually change this color to black because I think this green looks a little ugly. And I'm going to go into my node processing and set the debug equal to false, so that way they won't pop up messages each and every single time. Bam. Oh, see, it avoids that. Nice. And also notice that when I go back and forth, it cuts down here before it gets as close as it can to this block, because you know, it could have gone all the way 10 5 and then cut down here, but it knows that it can't do that because that's cutting a diagonal, so that doesn't work. Pretty nifty. Alright. Let's try and play around with this some. Let's see if I add an island in here, do that, and I'm going to add some things to make this a little bit trickier. I did a spiral type thing once, and that looked kind of nifty. Let's try that. So, let's try and throw some harder things at it. See, it finds the path just right. If I go here, it finds the path. Pretty neat. It feels pretty magical watching them go like that. And just out of curiosity, I'm not exactly sure what's going to happen now, but if I click inside the island, woohoo, we have found an edge case. You know, I don't actually think that this error is because of the island. I think it's because we're on the edge of the map. Let's test that. So if we navigate over to the edge of the map, and if I click here, oh, maybe it's only the top edge. No? Is it the island? Yep, it's the island. It is the island. Interesting. I don't think I've tested it with the island in my previous things. Let's hope it's not too big of an error. Out of range. Okay, let's turn debug back on, so that way we can see where exactly it messes up, because it could be anywhere in its logical thinking that it could have messed up. Let's head over to there. So it's trying 3 5, which is good. Then it's 3 5 trying 4 5, and 5 5 is trying 5. And okay, good. And now we're kind of running. Well, now it's going everywhere. A star can be inefficient in this way if you don't check for islands, because it doesn't. A star can be efficient if you don't check for islands, because it'll just keep looking. It doesn't know if there's an island, so it'll literally search through every single block. Okay, and so you can see it's going on for quite a while. And I'm assuming that it breaks once every single thing is on the closed list. Okay, well, yeah. It wasn't, we just determined that wasn't any time too early on, I guess. It definitely goes on for a while. Alright, so let's think what happens. So, we add to the closed list, right? And then here we check if something's on the closed list. So, what happens when every single one of these is on the closed list? Well, that would mean that, okay, this should be on the, this shouldn't have any problems. If it's on the closed list, it's on the closed list. This shouldn't have any problems because I and J are bounded in here. I may have messed up there, but I don't think so. This won't even be ran if everything's on the closed list, because whatever we have will be closed, so not closed will be false, and making this whole thing false. Alright, what else is there? Min f equals -1. If everything's on the closed list, that means that Okay, everything has gone through this process of being selected as the F, which means that the F should be empty. And then F equals -1, it should say, sorry, can't get to work. But that's not what's happening. So one of the assumptions I made just now is false. Okay, looks like we are going to get a good debugging problem. Okay, I'm going to go in here and set debug equal to false because it doesn't look like those messages helped me too terribly much. Okay, let's look at the error again. Where exactly is this happening? At line 19, and we're checking 815, which is out of range in 2015. Okay, let's go to line 19. I'll keep this open. I'll look over you. Let's see, so line 19 in this algorithm, what is that? I see. Alright. So, let me see if I can pull out my PowerPoint and give an example of how what's up. Okay, so we know that cur x is in range. We know that j is in the range. We don't know that cur x and j together are in the range. Okay, we know ij is in the range, but we don't know if these coordinates are in the range. Let me see if I think of a case where that would work. I think it'll always be in the range. Because that code's only called when we're going diagonal, so if we're here and we're trying to go here, then it will check those two places. Let's see. Is there a case when the diagonal can be in the field, but these two corners will not be in the field? I really don't think there is. That's where the error is happening. Let's see. It says here that it's trying to get 815. So this isn't quite accurate to our board. Oh, actually, it's on this first one that it's messing up. So it's checking a diagonal, which shouldn't be checking. Okay, so it says the range is 20 to 15, which means that it's 20 wide and 15 tall, I suppose. And we're all the way on the bottom. So I think it'll be useful for me to see these messages, but I don't want to have to click through them until the end, because that would be difficult. So what I'm going to do is I'm going to change the show debug message. Alright, which means they're going to pop up in this thing and they're not going to have their own window. So it should just scroll through them. I guess islands are a good way for testing out problems because it literally goes to every single node. Okay, that's disappointing. I didn't get anything in this window. I should have totally got some stuff in that window. Okay, my message didn't show up because I had debug set false. And set those equal to true, and now they should show up. I click there, and now I show. Okay, so we're on 513, and we're trying to get to 914, and this gets printed out down here. So when the error comes along, we've already gone this code. We've already changed it to 914, and we've bumped up to where's line 19 to here where the error happened. So we're on 914 when this error happens, and from 914 it looks like we're trying to get to 815. So we're on 914 and we're trying to get to 815. We're trying to go over there. Let's go through this and see why that would be. So let's try the test case. So in this case, our cur x is equal to 914. So okay, 9, and our cur y is equal to 14, and then our I is equal to 8. Our j is equal to 15. J shouldn't be reaching 15 because oh, there we go. That's it. 15 is a lower bound. It shouldn't be reaching the lower bound because we have it bounded in here, but we have it bounded by the width, even though j is a vertical thing. So that should be height, and since the width is greater than height, then there we go. All right, that was refreshing. Now we're prepared for it to work perfectly. Bam. No more left. This is actually a surprisingly small list. I thought it would go through every single one of them. Let's try it again with show message instead of show debug message. I should get this message and it should basically go through everything. Oh, blah, 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 blah. My bad. I'm an idiot. I put this debug stuff up here, but I didn't get rid of it. That should try everything, so it goes to Trevor, and then eventually it'll give up, and nothing happens. Okay. Alright, that took a little. So yeah, I guess I was right. We were finished, which meant we were 50% way through the tutorial, because all the debugging had yet to take place. Okay, let's turn this debug off, and let's take a few more moments to kind of enjoy our pathfinding algorithm. Now if we click it, we don't notice it. So this is actually, like, you saw how many operations it went through, but this is actually still a relatively small field. So even though when I click here, I'm going through every single one of these nodes, it doesn't block up the game. Let me see if I can do it really quickly. So, I mean, we always know computers are fast, but it's things like these that kind of gives us a true realization of how fast they are. It's really weird. I feel like that's not the optimal path. Oh well, you guys get the concept, and we have a relatively well-working program. Okay, good. Okay, so to finish off, okay, that's really bothering me. Why on earth is it doing that little thing right there? We're not done yet. Alright, so unfortunately I lost the very last part of that video, so I'm re-recording this. That last error though, that took me about a half hour to finish. That was very frustrating. I think it has record in my book as the most frustrating error I've ever had. I did get the recording of all that, so if you want to see about a half hour of somebody just hating life, then that video is just for you, and I'll have a link in the description for that. Hopefully it might also be good for some of you if you want to kind of see more in depth for the debugging process. So, when you check that out if you wish, here's what the error ended up being. This top one is what I had, this bottom one is what I should have had. So, this parenthesis screwed it up, because up here it saw this as the key I was looking up, and of course that's true, it's 1, if it's false it's 0, so it's odd that looking up the key, the index 0 or 1, and that's all it look up, and that completely messed everything up. Anyway, so that's that. It should run perfectly now. Thank you guys so much for watching. I've edited most of this already, and it's more than 2 hours long, so you could have watched a movie, you could have done anything, but you decided to sit here and watch my tutorial for 2 hours, so thank you guys so much. I'm curious to see how many of you guys actually made it this far. So, you know, if you're watching this, and if you made it to this point, you're listening to me, go ahead and type a comment below and type down, "I feel like I just had a lovely cup of tea, which I received from the ancient Taoist temple on top of Mount Huashan." Alright, I'm curious to see how many of those comments I see. I wouldn't be at all surprised if it takes years for one of those comments to pop up. But who knows? Prove me wrong. We'll see. Alright, so yeah, that is the end of this tutorial. As I said in the beginning, this could be done in pretty much anything, as long as you have a decent understanding of your programming language of choice. So yes, it works in any programming language. Most programming languages have some implementation of maps, priority queues, and lists, and all that. You just have to look them up and you'll find them. And most of them are quite a bit better than GameMaker's as well, so there's that. So, this video was done using a grid-based system for A-star pathfinding algorithms, which is what I did in my algorithm explanation. However, I made a second video, if you guys saw that, talking about how to implement them using graphs, which originally is what I was going to do this, but it's even more complicated than this. It's about, I think it's like twice as much code, or at least 50% more code, and we use some more data structures and stuff. So if you're interested in that, I've included the source code to that in the description. It's a little bit faster than this one, and it will actually get accurate paths. It's not restricted to grid-like movement. It will get like the most accurate path. So you can check that out in the description if you want to see that. So that is all for this tutorial. Thank you guys so much for sticking with me for the full feature film, and I look forward to seeing you guys very much in my future tutorials.